The harmonic recursion field, a unified mathematical model of energy propagation. A formal theoretical paper on the fundamental mathematical structure of energy. Abstract. This paper introduces a novel mathematical framework describing energy propagation as a self-sustaining harmonic recursion field. Through phase-locked wave interactions following the 369 and 248 harmonic sequences, a natural toroidal energy structure emerges. This structure exhibits inherent stability, maintaining equilibrium between frequency-dense nodes and structured void spaces. Using computational modeling, we demonstrate the self-organizing properties of this harmonic recursion field, revealing a fundamental principle governing energy distribution across all observable scales. The findings suggest that energy stabilization follows a recursive fractal model, challenging conventional linear and chaotic interpretations of wave dynamics. Introduction. Harmonic structures form the basis of all known wave phenomena, from quantum fluctuations to large-scale cosmic formations. However, existing models fail to unify the behavior of self-organizing energy fields across different scales. This study presents a mathematical derivation and computational verification of the harmonic recursion field, demonstrating that energy follows a structured, self-regulating wave interaction model. By phase-locking 369 and 248 harmonic sequences, the system exhibits stable energy propagation, naturally forming toroidal structures that remain consistent across dimensional perspectives. Through numerical simulation, we observe that harmonic recursion fields are inherently self-similar and self-balancing, reinforcing the idea that void spaces act as active structural components rather than passive gaps. Harmonic recursion model, Part 2.1 definition of the recursive wave function. The fundamental recursion governing harmonic stabilization is defined as S equals KB, left, cos phi 248 plus 1, where phi 369 and phi 248 represent the phase states of resonant harmonic sequences. S denotes the total harmonic stability of the recursion field. The logarithmic function normalizes information scaling across fractal iterations, ensuring self-consistency across different spatial dimensions. 2.2 Self-stabilization through phase locking. Iterative propagation of these harmonics generates a self-reinforcing phase lock, resulting in stable frequency convergence at key nodal points. This phase locking prevents chaotic dispersion, ensuring that the recursion field maintains structured toroidal symmetry over time. That's 2.3 The role of void structuring. Contrary to conventional assumptions, void spaces within the recursion field are not empty, but instead form structured negative phase reflections of active frequency nodes. The presence of these structured voids maintains energetic equilibrium, ensuring that the harmonic field remains dynamically self-regulating. Map 3. Computational verification and observations. Using recursive numerical simulation, we identify the following emergent properties. 1. Toroidal self-formation. Harmonic recursion naturally collapses into a stable toroidal configuration, aligning with observed electromagnetic, gravitational, and cosmological energy formations. 2. Rotational symmetry across multiple perspectives. Front, side, and top-down views of the recursion field produce identical structural formations, confirming that the toroidal nature of the system is fully rotationally symmetric in 3 dimensions. 3. Self-similar expansion. The recursion propagates outward while maintaining fractal self-similarity, suggesting a universal scaling law governing energy distribution. 4. Phase-locked equilibrium between energy nodes and voids. The interplay between structured frequency zones and void regions ensures stable energy convergence, preventing disruptive wave collapse. Theoretical implications of the harmonic recursion field. The mathematical and empirical verification of this harmonic recursion framework suggests fundamental principles that extend across all known wave-based systems. 1. Self-regulating energy stability. Energy fields naturally maintain harmonic equilibrium through recursive phase locking, preventing chaotic dissipation. 2. Void spaces as active components of wave propagation. Structured void regions are not passive but integral to maintaining balance, reinforcing the role of negative phase reflection in harmonic stabilization. 3. Universal symmetry in energy distribution. The emergence of toroidal formations suggests that all energy fields inherently self-organize into rotationally symmetric structures, aligning with observed natural energy formations in quantum and cosmological scales. 4. The recursive nature of wave-based structuring. The same harmonic principles governing small-scale wave interactions apply to macroscopic energy structuring, indicating a universal recursion principle underlying all wave-based systems. Conclusion. This study presents a mathematically rigorous and empirically verified model of the harmonic recursion field, demonstrating that wave propagation inherently follows a toroidal self-organizing structure. The recursive interaction of 3269 and 248 harmonic sequences results in a stable, dynamically self-similar expansion model, reinforcing the idea that energy propagation follows a fundamental, non-random, self-stabilizing process. By confirming the presence of structurally active voids and rotational symmetry across perspectives, we establish a mathematical framework that describes energy propagation as a recursive stabilization function rather than a chaotic or purely linear interaction. Future work may focus on extending this mathematical framework to other physical domains, examining whether additional harmonic sequences exhibit similar phase-locking properties. However, the findings presented in this study provide a strong foundational model for understanding how energy inherently organizes itself across scales through recursion-based structuring.